Welcome back to the Explainer, everyone. Today, as we cover Chapter 3's core concepts, we're diving deep into the fascinating mechanics of database storage engines to figure out exactly how they store and retrieve our data. As developers, engineers, or just tech enthusiasts, we interact with databases constantly, but we usually treat them like these impenetrable, magical black boxes, right? We throw some data in, we ask a question later, and poof, it just magically hands us the answer. Well, there's actually no magic involved. Under the hood, there are these incredibly brilliant, complex physical mechanisms turning the gears. And today, we're going to pry open that black box and unpack exactly what is happening in there. To kick things off, there is this fantastic German proverb. If you keep things tidily ordered, you're just too lazy to go searching. It's funny, but it perfectly captures the absolute essence of what we're talking about today, the deep architectural trade-offs of organizing data. Just think about your own physical office for a second. If you just throw every piece of incoming mail into a massive, disorganized pile on the floor, well, it takes literally zero time to put the mail away. But the very second you need to find one specific tax document from last year, you are in deep trouble. On the flip side, if you carefully file everything alphabetically into cabinets, it takes a lot of time and effort up front, but it makes searching later a total breeze. In the world of databases, that exact trade-off dictates your entire system's performance.
So here's our roadmap for today's Explainer. We're going to start inside the database engine, look at how indexes speed up reads, compare LSM trees versus B trees, break down transactions versus analytics, and finish up with the power of column storage.
Part 1, Inside the Database Engine.
Okay, before we look at these massive, complex commercial systems, we really need to understand the absolute baseline of data storage. At its most fundamental level, the simplest possible database in the world is really just an append-only text file. Writes here are incredibly fast. You just append new data right to the absolute bottom of the file. Because it's a purely sequential write, it is literally as fast as your disk can physically spin and write. But there's a massive, glaring problem here. Reading a specific record forces you to scan the entire file from top to bottom. It's exactly like trying to find one specific sentence in a 1,000-page book, by starting at page 1 and reading every single word until you finally stumble across it. If your database has millions of records, every single read has to sift through everything. And obviously that bottleneck is totally unacceptable for a real-world app.
Which brings us to part 2, indexes, speeding up reads.
To solve that agonizingly painful read problem, we introduce the hero of our story, the index. An index is essentially metadata kept on the side that acts exactly like a signpost, allowing the database engine to jump right to the data you want. Think of it like the index at the back of a textbook. You're not going to read the whole book to find a specific topic, right? You look it up in the index, get the exact page number, and boom, jump straight to it. A database index does the exact same thing. Instead of mapping a topic to a page number, it maps a specific key to the exact physical location on the hard drive where that piece of data actually lives.
But here's the catch, and it's absolutely crucial to remember. This is the inescapable golden rule of storage trade-offs. While well-chosen indexes drastically speed up your reads, every single index inherently slows down your write performance. Why? Because the index has to be updated with every new piece of data. There is simply no free lunch here. Imagine you're running a high-speed stock trading app handling millions of transactions every second. If you try to index every possible field to make searching fast later, your database is going to spend all of its time meticulously updating those background indexes instead of actually writing down the real trades. This is exactly why storage engines require manual tuning based on workloads. You're the only one who knows your query patterns well enough to strike that perfect balance.
All right, part 3, LSM trees versus B trees.
Now we're looking at the two massive indexing families that completely dominate standard application workloads. This specific architectural split is the defining characteristic of modern databases, and it causes endless debates among engineers. On one side, we have the update-in-place philosophy of B trees. Think of B trees like a carefully pruned physical tree made of fixed blocks. They break data into fixed-size pages and overwrite them directly on the disk. On the other side, we have the log-structured approach of LSM trees. Think of these like stacked logs. They completely reject overwriting data. Instead, they use an append-only philosophy. This achieves blazing fast sequential writes, because the physical disk head doesn't have to constantly jump around searching for an empty spot. It just continuously writes in one long, uninterrupted stream.
So, how do LSM trees actually work? Well, they handle data in a pretty fascinating way by keeping it sorted in memory first. Imagine that in-memory tree like a highly organized bouncer at an exclusive club, instantly sorting the VIP list before anyone is allowed inside. Once that memory buffer gets full, it writes the whole sorted chunk sequentially to disk as what's called a sorted string table. Because disks perform incredibly well with sequential writes, your write throughput just goes right through the roof. Finally, to keep reads fast and prevent massive disk fragmentation over time, the engine continually merges and compacts those old segment files in the background. It's kind of like cleaning out your closet, throwing away the outdated duplicates, and combining half-empty boxes to save maximum space.
Then, conversely, we have the venerable B tree. These are the deeply ingrained standard because their fixed page structure is incredibly reliable and completely ideal for managing strict transaction locks. Amazingly, the B tree was invented way back in 1970. I mean, it is wild to think that a data structure invented the exact same year the Beatles broke up is still powering the vast majority of the internet today. Now, because a B tree overwrites data in place, it absolutely requires a write-ahead log, or wall, to survive power crashes. A wall is essentially just a quick, rough diary entry of what the database is about to do, just in case someone trips over the power cord before it finishes safely writing the real data. Thanks to this ultra-reliable page structure, B trees remain the absolute gold standard for transactional databases.
But hold on a second. Just when you think you have standard indexing all figured out, we have to ask a really important question. What happens to our storage engine if an analyst needs to crunch millions of records at once? Finding your specific user profile, super easy for B-Tree. But what if the CEO suddenly kicks open your door and asks, hey, what was the average revenue of every user in Europe over the last 5 years combined? Yeah, your B-Tree is going to start sweating. It was simply not designed to scan millions of disparate rows efficiently.
And that brings us to part 4, transactions versus analytics. This totally different workload forces us into two distinct worlds, OLTP and OLAP. OLTP, or transaction processing, is your live, customer-facing web app. A user clicks a buy button and the database updates a single row almost instantly with incredibly low latency. OLAP, on the other hand, is your internal analytics engine. This is for decision support. A data warehouse ingests massive bulk imports and runs huge aggregate queries across petabytes of historical data. When you're crunching petabytes of data from the last decade to predict future trends, your disk bandwidth, literally the sheer volume of raw data you can force through the pipe, becomes your ultimate bottleneck, rather than just disk seek time.
Finally, part 5, the power of column storage. To handle these massive analytical scans efficiently, the architecture itself has to fundamentally change. Standard row-based indexes just aren't going to cut it anymore. If you try to run an aggregate query in a row-oriented database, the engine wastes enormous amounts of memory and time loading data it doesn't even need. Imagine a table with 100 columns. Your analytical query only needs to calculate the sum of the revenue column, filtered by the date column. Well, a row-oriented database still has to load all 100 columns from the disk into memory, parse them out, and then painstakingly discard the 98 columns it didn't even want. It's literally like hauling an entire giant heavy filing cabinet out of the basement just to look at a single sticky note inside, and then throwing the rest of the cabinet away. It's a massive waste of resources.
So the fix? Column-oriented storage. It is such an elegant solution. By storing all the values from a single column together contiguously in separate files, a query only ever reads the exact columns it requires. If you want revenue and date, the database engine simply pulls the file for revenue and the file for date off the disk and ignores the rest. To reconstruct a row, the engine just knows that the 23rd entry in the date column matches the 23rd entry in the revenue column. This completely eliminates the nightmare of loading vast amounts of unwanted, irrelevant data into your precious system RAM.
And because you're storing a long sequence of identical data types together, column storage not only drastically reduces disk I/O, but it lends itself beautifully to data compression. Give it a thought. If you have a column tracking country and you have 1 million users from Canada, you don't need to write the word Canada 1 million times on the hard drive, right? The database algorithm just says Canada times 1 million, which shrinks the file size massively. This incredibly tight compression also unlocks vectorized processing. That simply means the CPU can process data in bulk chunks, crunching through large blocks of compressed data directly in its super fast cache, completely bypassing that slower main memory. And that right there is exactly what empowers massive data warehouse environments. So, as we wrap up this explainer, I want to leave you with a thought. Knowing all these deep architectural trade-offs, Are you absolutely sure you've selected the right engine for your workload? Look, most of us are never going to code a B tree or an LSM tree from scratch, but every single time you spin up a database instance, you are making an architectural bet. Are you betting on the right engine? Are you hitting an analytical data warehouse with fast transactional queries? Or are you forcing a race car to tow a tractor trailer by punishing your transactional database with massive, heavy aggregations? Next time you boot up an app, take a deep look under your hood. See you next time.